Assalamualaikum warahmatullahi wabarakatuh. So, for this video, we will look at the introduction on the one-dimensional wave equation. So, right now, based on a case of a string, okay, take note, a string with both ends are fixed. That means here, let's say a person, two persons hold the string, for example. So the end are fixed. Okay, there might be a vibration. Okay, here like this. Okay, this is what we are trying to find. We are trying to find the disposition. Okay, so consider a string of length L stretched between the 2 points. Okay, for example, like I explained earlier. Suppose that the left end of the string is at point x equal to 0. Okay, while the other end is at x equal to L. For example, it means the distance between the initial position with the end position. Okay, so the goal is to find the displacement UST. This is what UST refers to, the displacement, okay, of the string at any point x and at any time t. Okay, so here, in order to develop mathematical model, the following assumptions are made. The first one would be the string here is perfectly flexible, okay, and has constant linear density and constant tension, okay, and there is no other force acting on the string. That means there is no third force that interrupt the phase, the flow, okay, and then the gravity is negligible, okay. The displacement UST is very small in comparison to the length of the string. Okay, for sure the displacement should be small to the length of the string. So let's say you have from 0 to 2, it would be impossible for the displacement to be high as the distance between the initial and the last end. Okay, and then with these assumptions, the motion of the string is governed by this formula. Okay, alpha squared USX equal to UTT, where x is between 0 to L. Okay, and since both ends of the string are fixed, the boundary conditions are as such. Okay, the first one will be U0T equal to 0. That means at the initial, the displacement will be 0. And ULT is also equal to 0. That means at the end, the displacement will also going to be 0 because it's fixed. Okay. And for t greater than or equal to 0, for sure t should be positive. Okay. And given that the initial position of the string is fx, okay, and the initial velocity of the string's motion is gx, this implies that the initial conditions are as such. Okay. US naught equal to fx and UTS naught equal to gx, where x between 0 to L. Okay, I repeat. Okay, fx is the initial position of the string, and then gx is the initial velocity of the string. Okay, so that's why we need to differentiate with respect to time. Remember, distance over time is the velocity. Okay. And then next, by combining equations 8, 9 and 10, these three equations, okay, the motion of the string can be determined by solving the following initial boundary value problem. Okay, this would be it. Okay, the whole thing that has been simplified. Okay, everything that I have highlighted are here. Okay, that means the equation will be alpha squared USX xt equal to UTT xt for x between 0 to L and t must be greater than 0. Okay, subject to the boundary conditions. Okay, this is the function. Okay, and the boundary conditions is U0t and ULT must be equal to 0 because the displacement should be 0. Okay, for t greater than 0, and the initial conditions US not equal to fx, the initial position, okay, of this string, okay, and UTS naught, the velocity is equal to gx for x between 0 to L. Okay, next. The solution for the wave equation. Okay, as we can see earlier, okay, the equation is actually this one. Okay, UTT equal to alpha squared USX. Okay, and here, okay, we need to let UXT equal to x of x times T of T. Okay, this is the first one that you need to do. And then by using partial differentiation, okay, partial differentiation, UXX is equal to x double prime x T of T. Okay, we hold T as constant. Okay, that means we just differentiate x. Okay, function of x. And UTT is equal to x of x T double prime of T. Okay, and then we substitute both equations in this equation, in the wave equation. Therefore, UTT here will be x of x T double prime T equal to alpha squared x double prime x T of T. Okay, I hope you get it until here first. Okay, the next one would be, since the functions here are independent to each other, okay, since they are not intertwined by each other, okay, so they must be equal to some constant rho. Okay, to some constant p, not rho, p. Okay, so this is why we write the p the same as in the heat equation. Okay, that means one thing that you need to note, the constant should be placed at t. Okay, once again, the constant should be placed at t. Okay, it can be in the x. Okay, it should be placed here. Then next, equation 12 here, this one, leads to two ODEs. Okay, the first one will be this part, where T double prime T over alpha squared T of T is equal to P. So by rearranging, okay, we have here P alpha squared T of T, okay, which can be written as such, okay, later on. Okay, for this one, it is from here, so x double prime of x over xx equal to P, which means x double prime of x equal to P, okay, x of x, okay, which can be written as such, right? So there are three possibilities for the value of P. Okay, the first one would be when P equal to 0, which means here x double prime x would be equal to 0 because it is 0, and so does T double prime T equal to 0. Okay, and solving these equations, we will get x of x equal to this and T of T is equal to this, where UST is equal to A1x plus A2 times A3T plus A4. Okay, let me show you how it comes to this term. Okay, because it's gonna be the same, just different constants. So that means when we integrate x double prime x with respect to x, means that we integrate 0 with respect to x, so we will get A1. Okay, this one is x prime x. Okay, x prime x. When we first integrate, we will have x prime x. Okay, and then next, if you want to find x of x, it will be integrate a. Let's say we name it as A1 with respect to x again. So this will be A1x plus A2. Okay, that's how it comes to this term. And so that's for T. Okay, and next, as you can see, for P greater than 0, we suppose that P equal to lambda squared, because anything power of 2 is equal to positive. Okay, positive constant. Okay, so right now it will be this type. It will change into these equations. Okay, we will be using the characteristic equation, or also known as auxiliary equation. So here it will be m squared minus lambda squared equal to 0. Here it can be factorized into m minus lambda, m plus lambda equal to 0. Therefore, m equal to lambda and negative lambda. Since we have two distinct root, so x of x is equal to this, and T of T is equal to this. Please mind, there is negative there. Okay, and so that's here negative. Okay, therefore UST, please do a bit of correction in your module. Okay, so UST is equal to A1 exponent lambda x plus A2 exponent negative lambda x multiplied with A3 exponent alpha lambda t plus A4 exponent negative alpha lambda t. Okay, please do a bit of correction here. Okay, So next, suppose that P is less than 0. Okay, that means we let P equal to negative lambda squared. Okay, because lambda squared is positive. We want P, the value of P should be negative, so negative lambda squared. And hence the equation will be as such. Okay, let's try for T double prime. So here it is M squared plus alpha squared lambda squared equal to 0. Using the quadratic formula, you will obtain M equal to plus minus alpha lambda. Okay, when you use the quadratic formula. Okay, alpha lambda I. Okay, complex number. Okay, so that's why here it will be S of x equal to A1 cos lambda x plus A2 sin lambda x. And then next, okay, T of t is equal to A3 cos alpha lambda t plus A4 sin alpha lambda t. Okay, and UST is the multiplication of S of x and T of t. Okay, and please note that we have to consider that the solution which is consistent with the physical nature of the problem. That means it follow the boundary conditions. Okay, since this is the problem of vibration, okay, vibration of a string, the displacement UST here must contain trigonometric terms. Therefore, the solution where P less than 0 is the only suitable solution. Because this is a displacement involving string. So, the shape of the displacement should be like this, right? So, this is the same as trigonometric functions figure. Okay, the figure for trigonometric functions. That's why we only consider the trigonometric terms. Okay. Okay, now, by the boundary conditions that we have, the first one will be when u0t equal to 0 here. So that means s0t of t equal to 0. Okay, therefore s0 equal to 0 and t of t does not equal to 0 for any arbitrary t of t. Okay, so u0t is actually a1 cos 0 plus a2 sin 0 equal to 0. Okay, therefore here is 0, a1 cos 0 is equal to a1. That's why we have a1 equal to 0. So hence s of x is equal to a2 sin lambda x. Okay, for the next one, ult is equal to xl t of t equal to 0, which means xl equal to 0. Okay, and here is the same for arbitrary t of t, which means t of t does not equal to 0. Okay, and therefore s of l is equal to a2 sin lambda l equal to 0. The reason behind it is because here we have s of x equal to a2 sin lambda x, right? So it will be a2 sin lambda l equal to 0. Okay, a2 does not equal to 0 because it is a trivial solution. Therefore, sin lambda L is equal to 0, which means this one is equal to sin n pi. Okay, lambda L is equal to n pi, which means here lambda is equal to n pi over lambda. N pi over L for some n equal to 1, 2, and 3 until infinity. Okay, therefore here s of n would be s of n of x is an sin n pi lambda n pi over L x. Here we change lambda into n pi over L, and tn of x is equal to b1 n cos alpha n pi L t plus b2n sin alpha n pi L t. Okay, and u and xt is a multiplication of sn and tn. And for this, it's compulsory for you to write n equal to 1, 2, 3 until infinite dot dot dot. Okay, where an here is simplified into an plus b1n, and bn is an times b2n. Okay, actually if we refer here, it should be a to n here. Okay, because this is A2, right? So it should change actually into A to N. Okay, but it doesn't matter much. Here is A to N, so here maybe you can change it to A to N. A to N. Okay, so next, by using superposition principle, okay, we can write this, all of this in terms of summation. Okay, so UST equal to summation from N equal to 1 until infinity. Okay, that's why we use summation here. Just rewrite everything. Okay. Okay, next, by using the initial conditions, we can determine the value of AN and BN. Okay, when we substitute the U as not equal U as 0 equal to Fx, we will have this equation. Okay, because it is the substitution of here, T equal to 0. Okay, that means U as not is equal to summation N from 1 to infinity AN cos 0 plus Bn sin 0, okay, here, and then sin N pi x over L. Okay, as you can see, sin 0 equal to 0, so this part we're going to be 0. Okay, and then cos 0 is equal to 1. That's why it can be written as such. Okay, and this is the same as the Fourier sine series. Okay, and therefore AN is equal to 2 over L, integrate from 0 to L, fx sine and pi x over L with respect to x. Okay, the last initial condition is UTST, the velocity. Okay, so we need to differentiate UST with respect to T. Okay, this is the UST. Okay, differentiate, we just hold the part for the x, the coefficient in x as constant. So we need to differentiate the first and second term. So here it will be negative alpha and pi over L AN sine alpha and pi T over L plus alpha and pi over L BN cos alpha and pi T over L. Okay, and with the substitution of UT as not as 0 equal to GX, we will have this equation. Okay, because I just write it on top of the equation, it will be summation M from 1 to infinity negative alpha and pi over L AN sine 0. This one should be 0, right? Anything multiplied with 0 going to be 0. And then alpha and pi over L BN cos 0. Cos 0 is equal to 1. Okay. And this one should be hold the same. The same here. Okay. We got it. Okay. As you can see, since this is sine, okay, sine, that means we are going to use the Fourier sine series again. Okay, for this one, this will be the coefficient at the front, right? So that's why we let AN equal to this. Okay, but for the last one, it should be this part, this constant here that we are trying to find. Okay, alpha and pi L BN equal to 2 over L integrate 0 to L GX sine and pi x over L with respect to x, where Bn is equal to this as such. Okay, the reason behind it, okay, please recall the thing that we find, that we calculate before, for Fourier sine series is fx equal to summation N from 1 to infinity Bn sine N pi x over L, right? So Bn is actually equal to 2 over L integrate 0 to L fx sine and pi x over L with respect to x. Okay, so we consider this coefficient to write at the front, right? That's why here we need to write this term at the front. Okay, that's all for the introduction, and we'll see again in the example. Okay, thank you for your time. Assalamualaikum.